The next distribution that we are going to talk about is Poisson distribution. And we are going to find out the moments and moment generating function, characteristic function of Poisson distribution, very similar to how we have done the binomial and Bernoulli in the last video. Right, so we'll start by writing the probability mass function of Poisson distribution, which is given as e power minus lambda power x by x factorial, where lambda is called as the Poisson parameter. Right, now how do we write the moment generating function? I'll quickly go to the moment generating function without trying to find out the mean by integrating x times the PMF. So rather than that, I try to find the moment generating function, and from there I'll differentiate it once and then try to get the mean value twice to get the mean square and subsequently variance. So this is summation, because this is discrete random variable. Summation x runs from 0 to infinity e power tx of x, which is e power minus lambda power x by x factorial. Right, so I'll be pulling out the constant. The constant here is e power minus lambda. Rest all are dependent on x, so x runs from 0 to infinity. This is going to be lambda e power t, isn't it? Lambda e power t whole power x by x factorial. Lambda e power t whole power x by x factorial. Now you can quite well see, we can quite well write the Taylor series for this. So this is going to be e power minus lambda, and this will be 1 plus lambda e power t whole power 1 by 1 factorial, right? Plus after expanding it, lambda e power t whole square by 2 factorial, so on and so forth, plus lambda e power t whole power n. I'll stop till n factorial, and then that continues. So this is the expansion that we have, and this is in, as we can see, that it is the Taylor series expansion. And this is the Taylor series expansion where you have e power x, where x is lambda e power t. So this is going to be e power x, which is e power lambda e power t. Right, so e power, going forward, the moment generating function is going to be the moment generating function mx of t is going to be, we have an e power minus lambda on the outside of the brackets, and the new one is e power lambda e power t. So I'll be pulling out e power lambda as common, and this is going to be e power t minus 1. So this is our moment generating function, and we can very well write our characteristic function, because we very well know that if we replace t by j omega, it's going to be our characteristic function. So this is our characteristic function. All right, and then we start finding the mean value. Mean value, we know that it is you differentiate the moment generating function once, and then substitute the value of t to be 0 wherever it is present. So I'll try to do the same thing, d by dt of e power lambda times e power t minus 1. Then towards the end, I'm going to substitute t is 0 once I'm done with that. So this is going to be lambda e power t. I think we're going to get e power t, lambda e power t outside, times, because minus lambda, it's going to be a constant. There won't be any differentiation, and it is followed by e power lambda e power t minus 1. Right? And now in this, we got to substitute t as 0. When we substitute t as 0, this becomes e power 0, e power 0 is 1, e power 0 is 1. So we are left with lambda. So the mean value is lambda. That's what we've got. And going forward with the mean square value, we're going to differentiate the moment generating function twice. Mu 2 dash is how we represent it. We're going to differentiate it twice and then equate t is equal to 0. So this is the expression that we have prior to substituting t as 0. So we're going to differentiate that and then try to substitute the value of t as 0. So it's going to be d by dt of lambda e power t times e power lambda e power t minus 1. Right? This is how we differentiate it. And once we go forward and differentiate it and then put t as 0, I'm sure all of us would, all of you would be able to easily do it. Once lambda e power minus lambda is anyways pulled outside here, it being a constant, and you're left with e power t and e power lambda e power t. That's what you'll be left with. Upon solving it completely, you'll be getting lambda square plus lambda as the mean square value. Please try to work it out, do it yourself. I think it's no big deal. So it is lambda square plus lambda, and this is mu 2 dash. Now we've got the value of mean as lambda, and mean square value is lambda square plus lambda. So if you want the variance of x, the Poisson parameter for the Poisson distribution, it is mean square value minus the square of mean. So this is going to be lambda square plus lambda minus lambda square. So we are left with lambda. That's the value of the variance. So consolidating everything into one place, when we talk about the moment generating function mx of t, where x is the Poisson distribution, where x is a random variable which adheres to Poisson distribution, the moment generating function is e power lambda times e power t minus 1. The characteristic function is e power lambda e power j omega minus 1, right? And the mean square value, the mean value is going to be lambda mean square. The raw moment is lambda square plus lambda, and variance is again lambda. So this is the final value that we've got for Poisson distribution, right? So we are left with Gaussian distribution in order to find, which we will see in the next video.